Good morning, everyone, and thank you for being here. Today, I'm going to present the results of my research in rare elements and at the Thacker Pass deposit as a lithium sedimentary deposit in northern Nevada. And here's a picture from McDermott caldera, the western margin of McDermott caldera, from Calavera Canyon and the Thacker Pass. In this presentation, I will give a quick overview of the study area, including its location, geological setting, rare earth occurrence and distribution, and we'll wrap up with some implication of this study. Lithium and the rare earth elements are generally considered to be among the most critical metal and minerals. And McDermott caldera hosts a number of sedimentary clay-type deposits. The more well-known is the Thacker Pass, with our resources of 61 million tons of lithium carbonate equivalent, and McDermott Lithium project in the northern part of McDermott caldera in the Oregon border. They have resources of 21.5 million tons of lithium carbonate equivalent. Our work is focused at the Thacker Pass in the southern part of McDermott caldera. This study presents new data on the distribution of cerium, lanthanum, neodymium, and praseodymium in the world-class Thacker Pass lithium deposit. Despite the critical importance of these rare earth elements, the occurrence of these elements in this lithium sedimentary deposit has not been well characterized. Well, McDermott caldera is located in the Humboldt County in Nevada, around 70 miles of north Winnemucca, and approximately 240 miles northeast of Reno, Nevada. The caldera is bordered by the Bill Creek Mountains and the Kings River Valley to the west, and the Santa Rosa Range and the Queen River Valley to the east. The McDermott caldera has dimensions about 40 by 30 kilometers, and it's a part of the large igneous province that produces the Columbia River basalts and other silicic calderas of the Yellowstone hotspot tract. This area is sparsely populated and used primarily for ranching and farming. The McDermott caldera is commonly considered the point of origin of the Yellowstone hotspot, as you can see here. This caldera formed during the eruption of 16.4 MA McDermott tuff. This eruption generates this shape, 40 by 30 kilometers. The total collapse was no more than 1 kilometer, and the total erupted volume was around 1,000 cubic kilometers, of which 40 or 80% is intracaldera tuff. Most of the volcanic rocks exposed in the McDermott caldera on its margins are middle Miocene. The caldera underwent a post-collapse resurgent dome between 16.4 and 16.1 MA. The tufaceous sediments, the host rock of lithium mineralization, accumulate in the caldera basin starting immediately after initial collapse and lasting at least 15.6 MA. The youngest rocks in this caldera are minor olivine tolate lavas and placed at 14.9 MA. If you want to know more about the evolution of the McDermott caldera, I highly recommend Henry et al. 2017. The Thacker Pass deposit is hosted in these lacustrine sediments, as you can see here in this image. These are a typical drill core from Thacker Pass. These layers of clays, volcanic ash, and carbonates. These carbonates some texture of nodules or fireworks texture like this. And at Thacker Pass, we identified 3 mineralization zones that is split from the top in smectite zone, and in the middle of the deposit, a transitional zone is a mix between illite and smectite, and in the bottom of the deposit, we have the illite mineralization zone. So during this research, I studied the geochemical database from Lithium Americas, focused on rare earth mineralization. Based on this statistical analysis, Thacker Pass has an average concentration of cerium of 52 ppm and average concentration of lanthanum and 21 ppm. As you can see here, lanthanum and cerium has a strong correlation in the deposit. And also we identified a negative correlation between lanthanum and cerium and lanthanum and lithium. Lanthanum and cerium and lithium and lanthanum and lithium. In order to understand this negative correlation, why cerium and lanthanum are weak correlated with lithium, I create this log profile between lithium, cerium, and magnesium-lithium ratio. Why magnesium-lithium ratio? Is because it's very difficult with lens to identify what is smectite or illite or transitional zone. As you can see here, when the magnesium-lithium ratio is more than 20, we are in the smectite zone at the top of the deposit. And as you can see here, this is at a transitional zone, and when the ratios are less than 20, we are in the illite zone. As you can see here, the cerium is in the top of the deposit, and the values decrease when we have more lithium contents. Although this concentration of cerium and lanthanum are low compared to lithium, as you can see here, we have an average of 2,000 ppm of lithium at deposit level. It's important to understand the mineralogy and deportment of these rare elements to further assess their extraction as a co- or byproduct in these deposits. What is the occurrence of these rare elements? These rare elements occur in these lithium clays, as you can see here, mainly filling pores in the clays in smectite and illite. They have fibrous habits, as you can see here, and irregular shapes and aneral morphologies with sizes ranging from 5 to 30 microns. And the most abundant mineral phase identified was basnasite. We have 3 types of basnasite enriched in cerium, lanthanum, and neodymium, and also monazite. These data indicate that these minerals assemblage comprise fluorocarbonates, as I said, basnasite and sinchicite, and also phosphate as a monazite. We create these ternary diagrams between rare earth elements in APM and carbonate and fluor to understand what kind of fluorocarbonate we have. And we identified basnasite and sinchicite. And also the same for phosphate as a monazite. Finally, a box diagram of this data we use to understand the concentration of major elements in monazite, basnasite, and sinchicite. As I said before, we have 3 types of fluorocarbonates. Basnasite enriched in lanthanum, basnasite enriched in cerium, and enriched in neodymium. And two analyses correspond to sinchite, and the phosphate is monazite. Many of the metals extracted as a byproduct as rated as critical and are vital to important and modern technologies, but are seldom reported as extracted commodities by the mining industry. For example, Lithium Americas performed this geochemical database, and they only study cerium and lanthanide, but we identify also neodymium and praseodymium in the deposit. These rare elements are essential for numerous applications in space engineering and energy sectors. In these lithium clay deposits, as I said, the rare elements are not the primary target for recovery, but we need to understand, we need to study during the exploration phase to understand if these minerals could be a byproduct in this type of deposits. There are over 100 rare minerals, but a very few of them have been successful, fully processed and extracted, and the most common is basnasite, and we have basnasite in this deposit. The potential of this lithium sedimentary system to host other potential core and byproducts require further assessment. We know we have more than the rare elements in McDermott and in Thacker Pass. We have rubidium and cesium as a co-byproduct. And this image belongs to Thacker Pass. The deposit, the lithium clays are located here, and these are the works for the foundation plan, for the metallurgical plant. And I just want to know Simon Howitt, Chris Henry, Carolina Munoz, and the geologists from Lithium Americas, the chief geologists Randall and Colin and Chad.